So for this one, we have a pretty standard inclined plane question. It's just going to have one extra step involving, well, okay, two extra steps, involving the formula we learned yesterday. And that is that the force of friction, be it kinetic or static, is dependent on the coefficient of friction and the normal force. Okay, the stronger either one of those, or the larger either one of those is, the greater the force of friction will be. Okay, we talked about how mu is basically how easily, it gets a factor basically that tells how easily the surfaces will slide past each other. And normal force is how hard are they being pushed together, right? Because both of those things affect how much friction there is. The example we used yesterday was throw in sandbags or hay bales or whatever in the back of a pickup truck with rear wheel drive. That keeps more weight over the back wheels, so there's more normal force from the road and thus more friction, okay, and that can help you to maintain traction. So if we're looking at this situation here, as we said, standard inclined plane question, right? We got our force of gravity here, which we calculate with m times g, okay, so 20 kilograms times 9.81, that'll be 196.2 newtons, okay, on that side. And then we can calculate both F parallel and normal force. But before I get to that, I want to identify the two forces that are acting in the plane that the box is going to move, and that is along the plane. So this would be F parallel, and this would be the force of friction. All right, so now that I know that, now I know I have to calculate both the sides of that internal inclined plane triangle, because I'm going to need F parallel, it's here, and I'm going to need normal force to get the force of friction. So I'll have to calculate them both. All right, so that means then F parallel, because it's the opposite side, will be the sine of 40 times 196.2. All right, so F parallel is going to be 126.11 newtons. All right, so F parallel is acting down the hill. All right, and then to get the normal force, it's the adjacent side, so it's the cos of 40 times 196.2. Okay, so that side's 150.30 newtons. Now that I have normal force, now I can calculate the force of friction using the friction formula, and then I'll have the force up the ramp. Everybody okay with the steps there? Okay, so just plugging in numbers here, that's going to be 0.185 times the 150 there that I calculated for the normal force. Okay, so I'll take that normal force there, okay, and multiply it by 0.185. So there are 27.81 newtons of friction resisting the sliding of the box that's on the ramp. Okay? All right. Now that I've got F parallel and the force of friction, do any of these other forces matter anymore? They don't. Okay? A very common mistake people make with inclined planes is when they calculate the net force, they start bringing these numbers back in. Remember, I only needed these numbers to get the two forces that are actually doing anything. Okay? F parallel is the net force of normal force and gravity. So it's already a net. I can put it in there. I don't need to put gravity and normal force back into a net force calculation. Okay? So my net force here is going to be the 126.11 F parallel plus negative 27.8, my force of friction. That will get me my net force. All right, so we'll take those two numbers. Okay, so I got 98.3 newtons of net force. All right, now that I've got that, now I can calculate the acceleration of the box. F net over m. 98.3 over 20. Okay, so that thing is accelerating at 4.9 meters per second squared down the ramp. Okay, everybody all right with that? So that friction formula doesn't really do anything to change how the question works. It just brings in an extra calculation or two. Okay, it's still all the same forces. It just, instead of giving you the friction, now it's making you calculate it. Right? So bringing in that extra step. Okay. All right, just to give you an idea here, there's kind of a chart here that tells you the coefficients of friction between two surfaces, okay? And you can see here, okay, coefficient of static friction is the bigger number, okay? Because that's the one that doesn't slide, right? Once you overcome it, then it's kinetic friction and it's easier. Copper on copper is one of the highest ones, okay? For whatever reason, copper does not slide past itself easily at all, right? And that's static or kinetic. Okay, steel on dry steel, okay, if you're ever trying to push two pieces of steel past each other, okay, that would be difficult. That is the problem faced by all internal combustion engines. Steel slides past steel as the pistons go up and down inside the cylinders of your engine. Okay, that's why they have to be well lubricated with motor oil so that they slide past each other more easily. Okay, if your car is out of oil, that's the coefficient of friction that it's going to start with, and then eventually it'll get to this one because your car will seize. Okay, it'll make this horrible sound, and probably pieces of steel will come flying out of it, and then oil will spray out, and then it will make a horrible sound that represents its death cry. Okay, that's not what you want to have happen. The oil light comes on, it doesn't mean keep driving. Okay, it means stop right now and put oil in me. Okay, steel on greased steel. I mean, look at this. You got oil in your car, does that number go down a lot? Okay, pretty significant, right? Dry oak on dry oak, I don't know when you would ever have that, but rubber tire on dry asphalt. That's why we use rubber for tires. It's got a high coefficient of friction with asphalt. Okay, but look what happens as soon as it gets wet. Okay, you have half as much friction when the road gets wet. Okay, little things like that, right? When it first starts to rain, you actually have slightly better, like before it starts to puddle and you can see it on the surface. Okay, it can actually be quite a little bit better in terms of friction. But once you've got rain on the road, like it's starting to look really wet, okay, then it's going to drop. Okay, dry concrete, also not a bad one. Okay, rubber tire on wet concrete, you can see it drops again. Look at ice. Okay, that is why you spin and spin and spin in the wintertime. The coefficient of friction between a rubber tire and ice is 0.006. Okay, you've got to be really careful with the throttle or you are going to be spin central, okay, and sliding down that hill into the person behind you. Don't be that guy. Also, don't be the guy that's so close behind that you get slid into. Yeah. Okay, curling stone on ice. Okay, even less, right? This is what makes curling challenging, is you got to get just the right amount of power on that, okay, to get it to stop when it gets to the circle. Okay, what's the point of the sweeping?
Make it speed up.
Well, it won't speed it up. That's only the throwing. You can both change its direction, but also make it go further. Okay, sweeping has two effects on a curling stone. Okay, you can steer it, not by actually pushing it with the broom, because apparently that's illegal. Yeah, if you touch it, it's a foiled rock.
Burned, yeah.
Burned rock, that's the word. Okay, but you can, what you're doing when you sweep is on curling ice, if you've ever seen it, it's almost rough.
It's pebbled.
Pebbled. They take a hose and they spray it and then it falls down and freezes onto the surface. It's kind of bumpy. Okay? When you're sweeping, you're melting those pebbles with the broom. Okay? And that creates a layer of water between the rock and the ice. Well, that interface has less friction than the rock right directly on the ice, so the rock will travel further. Okay? You can also steer it by only sweeping one side. Okay? If you sweep one side of the rock, that side of the rock experiences less friction, and it'll turn in to the side with more friction. So you can actually steer it by sweeping one side or the other, and it'll start to turn in the same way that if I'm walking along and I catch my arm on the screen, I turn towards the screen because that side of me slows down and the other side doesn't. Okay, making sense? When we get to the circular motion unit, we'll talk about why people end up in the pond out here. Okay, part of it is stupidity. The other part of it is physics and not understanding physics. Okay, it's all about friction. Okay, when we get to unbanked corners, okay, that's because of friction. Okay, that you end up in the pond. There's not enough friction to cause an acceleration that lets you turn the corner. Okay. All right, other ones here. Teflon. Teflon's pretty low, right? 0.04. Okay, and then if you've ever done cross-country skiing, like old skis, I think even to an extent some of the high-end new skis, okay, if you wax them, you change the amount of friction involved. Because if you're cross-country skiing, sometimes you need to be able to press on the ski and not have it slide if you're trying to go uphill. Okay, so you wax those skis, and then they'll give you different types of traction. Synovial fluid in your joints. Okay, so in any joint in your body, okay, there's a fluid in there. Well, you do. When you get old like me, there's less of it and it doesn't work as well. It's got a pretty low coefficient of friction, which is why your joints probably don't creak and crack and do other weird things. Okay, they will. It's called time, and it knows where you live. Okay, but that synovial fluid does break down over time, and the more you injure yourself, the more it decreases. But it makes your joints slide past each other very easily. Okay, you can actually get synthetic stuff. I get injections that have hyaluronic acid in them, and it acts as a replacement for that synovial fluid. And it can help the joint to slide better and catch less and make less disgusting popping sounds. All right, making sense? Just to give you an idea, some of the surfaces we might encounter on a day-to-day basis. All right. Okay, now this one is one that often comes up. Okay, I often have people ask, why are some tires wider than others? Okay, yeah, well, it's got a greater surface area, right? But you'll often see high-performance cars have very wide tires, whereas economy cars have very skinny tires. Okay, and there's often this argument that wider tires provide you with greater traction. Okay, and while there's a bit of logic to that argument, do you see surface area in this formula anywhere? Okay, all things being equal, a wide tire and a narrow tire in kind of any given situation for a very short period of time would have zero difference. Okay, it's just about the tire and the road. Okay, the mu and how heavy the vehicle is. When the tires get hot, that's where surface area starts to come into play, which is why you would see a high-performance car have wider tires. A wider tire allows more heat to be bled off into the environment, okay, versus a small surface area. Okay, so that is where that will come into play. Does that sort of make sense? Okay, so wider tires, if the tire is getting really hot, can make a difference, because a tire, if you get it too hot, will vulcanize. Okay? That basically means the rubber turns to a liquid and then is essentially burnt off. That's the blue smoke you see coming out of a car that's turning its wheels really, really quick. Okay? It's burning off those tires. It's vulcanizing the rubber and essentially burning it off. Okay, that's very expensive, by the way. Don't get in the habit of doing that unless you like putting new tires on your car all the time. Making sense? So wide tires do have that advantage. They will allow heat to dissipate and maintain their shape a little longer than a narrow tire, but that's only if you're really abusing them. Okay, most of the time it should make no difference at all. All right, I think that was all we needed to cover. Oh, right, this one, that's horizontal. I want to do one that's got an angle, not that one. Where's the one that has this? The one. Okay, I want you guys to copy this one down here, and we're going to walk through it together. This is about as hairy as a Newton's second law / friction question could ever get for you. Okay, so give me a minute to get this copied down, and then we'll go through it together. Okay, so this question involves vectored forces. It involves friction, mu, okay, because we've got the coefficient of friction here, okay, and all of that kind of stuff. You have a question like this on the Newton assignment, okay? So kind of paying attention to how this question gets solved could be helpful on that question. The other day we talked about how there's different ways to drag something along the floor or push it along the floor, okay? And we said that if we're kind of pushing down on it like this, it's at an angle, but I'm pushing down, it doesn't slide very easily because what am I doing to the normal force when I push slightly down? I'm increasing it. I'm pushing the desk into the floor harder than it would in this situation. That increases the force of friction. Okay? If I just push it horizontally like this, it slides a lot easier because now it's just the weight of the desk. Even easier still would be to take some of the weight of the desk off of the floor so that there's even less. Now it slides really easily because friction is even less because normal force has gone down. Does everyone remember that from the other day? Okay. That's what this question is talking about. So we've got a 20 kilogram block. It's being pulled by a slightly angled upward force of 200 newtons. Okay, so if I'm pulling this slightly upwards, that means I'm pulling forwards and up. Okay, so let's calculate some of the forces that are in this right now. Can we calculate the force of gravity pretty easy?
Yeah.
Okay, so force of gravity, okay, is just going to be m times 2. So that'll be 20 times 9.81. This is going to be 196.2 newtons. Okay, can't calculate the force of friction yet, but it's a mistake people will make on a question like this. They think, okay, I got the force of gravity, and this surface is level, so that means that I also know the normal force. Do I? I don't. If I was pulling this horizontally with 200 newtons, I would know the normal force because the normal force in gravity in that situation would be equal. But because I'm pulling this at an angle, I have a slight force that is also upwards, the vertical component of my pulling force. Okay? So this force vertical and the normal force have to add up to this number here. Would you agree? The box isn't moving vertically at all, is it? I'm just pulling it along the floor. Okay? So that means the upward forces and the downward forces cancel each other out. So what I actually have is a force vertical, that, normal force, which I don't know yet, and a force downward of 196.2. Looking at this, I know that force of gravity, normal force, and the force vertical add up to 0. I know that because the box is not moving vertically. Okay? This is why this question is hairy. It's not because of all the calculating that has to go on, it's because of all the reasoning that has to go on. Okay? Vertically speaking, there is no net force in this question because the box isn't moving vertically. It's being pulled along the floor. Okay? So, if this is true, that means that Fn plus Fv equals Fg. Because normal force and force vertical are up and Fg is down, and we know they add up to 0. Okay, so if that's true, can I calculate the force vertical right now? I can, because I know this force and I know the angle. All right, so force vertical will be the sine of 10 degrees times 200 newtons. It's not going to be very big, but it can't be. If I lift too much, I'll lift it off the floor, right? I can't lift too hard. All right, so that force is 34.73 newtons. Okay, should I also at this point calculate its horizontal component? I mean, if I'm doing trig, I'm going to need that number because it wants to know the acceleration of the box. The box is going to accelerate that way given what I'm seeing here. Okay, so I'll probably need to know how much of that 200 newtons is acting along the floor. So I should calculate at this point, okay, that horizontal component as well. So that'll be the cos of 10 times 200. All right, so that's 196.96. Okay, I still don't know what the force of friction is because I don't know what the normal force is. Can I calculate the normal force at this point? I can't, because I know that Fn and Fv add up to 196.2. Right? The box isn't moving vertically, so the upward and downward forces have to be equal. So the normal force will be force of gravity minus the force vertical. Okay, whatever is left is how much of the weight of the box is still sitting on the floor, okay, not being supported by the upward part of that 200 newtons. All right, so 196.2 minus the 34.73. Okay, so there's 161.47 newtons of normal force. Okay, now that I know the normal force, can I calculate the force of friction? Because I have mu, right? It told me what mu is right here. Okay, so force of friction is mu times Fn, so 0.255. times 161.47. Okay, so there's not a lot of friction, right? There's only 29.87 newtons of it. Okay, so when this is all said and done, I have a force forward and a force backwards. Agreed? I've accounted for all of the other forces. I've accounted for all the vertical forces. I know they add up to 0. Okay? I now know that of this 200 newtons here, 196.96 of it is pulling horizontally forwards. I know now that there are 29.87 newtons worth of friction acting backwards. Okay.
Did you put in the wrong number for the mu?
Did I?
Because all of us are here on a different number for friction.
Yes, I did. I put 0.185 for some reason. Nice catch. Okay, let's try that again. 0.255 times that number. I like that you guys are on the ball. Okay, 41.17. Let's do that again. Okay. 41 sorry, what was it? 817. Okay, so now we have the right number. Okay, so I've got the 41.17 newtons going backwards. I've got 196.96 newtons going forwards. Okay, I mean, in the end, regardless of the number, we have a force forward and a force backward, and we've accounted for everything else. Okay, have I now gotten to the point where I can finish my vector sum of all forces? Can I now calculate the net force acting on this box? I can. All of the stuff we've done up until this point is vector sum of all forces. Some questions involve a lot. Okay, so like, let's finish it, and then I'll show you what this would have looked like if we'd have drawn everything tail to head. Okay, like it's the reason we kind of do it this way is to simplify everything. Okay, so we've got our 196.96 going forward, so we'll take that number there. And we'll subtract that force of friction, the now correct number, okay, that we have going backwards. All right, so the net force here is 155.78 newtons forwards. Question wants the acceleration. What's my last step?
5 by 20.
Right, do F net equals m times a. The thing we said you do in every single problem you ever face with Newton's second law. Okay. Well, not minus, divided by 20. All right, so this thing is going to accelerate fairly quickly. Okay, forwards 7 point, what do we have, 2 sig digs there, so 7.8 meters per second squared forward. Okay, so this question is like the mother of all Newton's second law, sum of all forces kind of questions. Okay, if we'd have actually drawn a vector diagram of this situation, we would have had our 200 newtons, okay, and then we would have had gravity, 196.2, and then we would have had normal force, and then force vertical, and then like it would have been, those cancel each other out, and then I would have had force of friction backwards, and like it would have been a real mess to do all of this. Okay, everyone kind of follow me there? All right. So the reason we don't do it that way is it makes it difficult to actually do, okay, the reasoning part. It's better to have the free body diagram there to help you with the reasoning. Okay. All right. Yeah, you guys can do that one. Okay, give that one a try, then we're going to move on to Newton's third law. Okay, so let's have a look at this one. It's, again, pretty standard inclined plane problem. Okay, we're still going to have that same triangle. We're going to need all 3 sides of it in this question because we are given mu, not the force of friction. Okay, even though we're not given the force of friction, from the context of the question, we know that friction has to be resisting the rolling of the bike. Okay, if the bike is going to roll downhill, friction has to act opposite its movement. Okay, that's how friction works. So I need to calculate some forces here. I got to calculate the force of gravity first. So that'll be the mass, 80 kilograms times 9.81. All right, so we got 784.8 newtons on the hypotenuse. Okay, then we'll calculate F parallel and normal force. Parallel is the opposite side, so sine of 18 times 784.8. Okay, so we got 242.52 newtons acting down the hill. All right, we got to get F normal. It's the adjacent side, so cos of 18 times 784.8. All right, so we got 746.39. Okay, now that I've got that and mu, I can calculate the force of friction. Force of friction is mu times the normal force, so 0.300 times 746.39. Okay, so our force of friction is 223.917. Okay, I'm just looking at those numbers. Do I have a lot of net force going on here? Not much. this person must be on the brakes, would be my thought, right? They've got the handles, squeezed, and they're on the brakes, because there's very little difference in the up and down forces here, only 20 newtons for an 80 kilogram object. Okay, so this is a person who is trying to slow their descent. Are they still accelerating downwards? Yes, there's still more force downwards than upwards, but it's way better than just letting off the brakes and praying. Because yeah, if you're going down an 18-degree hill, that's actually a lot steeper than you think. Okay, like most roads are not going to be 18 degrees. That's really, really steep. Okay, so let's calculate our net force here. F net's going to be the vector sum of all forces. We've already accounted for all the forces under the ramp, so we don't have to worry about those. It's just F parallel plus the force of friction, with force of friction being up the hill. So take our 242 down the hill, subtract our up the hill. Okay, we've only got 18.6 newtons of net force in this problem, acting on 80 kilograms worth of bike and rider. So acceleration, okay, is going to be 18.6 divided by 80. So we're not talking about a super big acceleration here. So divide that number by 80 kilograms. All right, it's not a huge acceleration, 0.232 meters per second squared down the ramp. Now, that's not what the question wants. The question wants to know how fast they're going when they get to the bottom, which is 75 meters from where they start. Okay, so now, am I doing a unit 1 question? Yeah. Okay, I've got VI, VF, D, or sorry, A, VI, and D, and I'm looking for VF. So I'm thinking probably this formula. Okay, that's the one I've got all the information for. Okay, because I believe I heard somebody whisper, you got to square root that. Yes, you do. When you're looking for VF here, this is going to be a situation where you've got to go 0 squared plus 2 times 0.232 times 75 meters. All right, so when we punch that in, so square root of 0 minus, and then we'll have our plus. Okay, plus 2 times the 0.232, so that number with all the digits in it, plus times 75. Okay, so bottom of the hill, 5.9 meters per second squared, or sorry, 5.9 meters per second down the hill. Okay. Everybody with me there? Now, if that person wasn't riding the brakes, that coefficient of friction would be a lot lower, and that VF would be a lot higher. Okay? Questions on that one?
They did it wrong, but I got it right.
But if you got it right, I doubt you did it wrong. You must have just found another way to do it.
Yes.
It's usually more than one way to do something. What did you do different?
That's what I don't know.
Oh, okay. So did you use a different acceleration formula?
No, that's used.
I don't think you did anything wrong then. You just did it different.
Okay.
Nothing wrong with different. Okay. Okay, let's talk Newton's third law here. Okay, so if you got your notes package, it's lesson 7. We've already done stuff with Newton's third law. Okay, we just haven't talked about it on its own. Okay, normal force is the result of Newton's third law. It is the reactive force that is present in all situations where one other force is present. Okay, has anyone ever gotten in those big inflatable, like balls, and you run into other people in them? Okay, they're a ton of fun unless the person you're running into is way more mass than you. I learned that the hard way. Okay, because a buddy of mine from university and I got into those two things, and he was a university wrestler, so he's like 5'2", and square, like probably, I don't know, more than me. I won't embarrass either one of us by saying weight, but probably 1.5 times heavier than me, and which are much lower center of gravity. I mean, he was putting me all over the field in these things, and there's nothing I could do about it because he just had more mass than me. Right? Mass matters. You know, what do you do? I was faster than he was, but it doesn't really matter when you're in that ball and can't really run very well. Took all my advantages away. All right, so all forces act in pairs. That's one of the things we got to understand. Okay, like the essence of Newton's third law is that no force acts on its own. Okay, right now, sitting in your desk, there are a pair of forces acting on you. Gravity is pulling you down, the seat is pushing you up, and as a result, you don't fall. Okay, right now, the gravity pulls me into the floor pushes up on my feet, I don't fall. Okay, forces act in pairs. It's also why, not that any of you would do this, you can't punch somebody for free. Okay? If you hit somebody, are you going to hurt your hand? More than likely. Okay? Because when you hit them, they'll hit back. Not literally, like they might swing at you too, but okay, when you actually make contact with them, okay, you exert a force on them, and an equal but opposite force is exerted back on your hand. Okay? This is actually why in most martial arts, they don't use the hand for striking as much. Okay? What do they use instead? Well, that's still part of the hand.
Kick a lot.
Yeah. Use the heavy, hard bones of the body. Elbows, okay? Forearms, shins, knees, okay? Use the heavy parts of the body. If you hit something that's more massive than your hand, the forces experienced by both are equal, but the mass of your hand is probably less than the thing you struck. Okay? Pretty good chance you'll break your hand. Okay? So you shouldn't hit anyone, like, period. It's not a good idea. But if you did, okay, especially bare knuckled, you have a pretty good chance of breaking the bones in your hand because they're smaller and they're lighter than whatever it is you hit. Okay? Maybe you're one of those people who gets easily frustrated and you punch things. Okay? Don't punch hard things like walls. They're bigger and heavier than your little bones in your hand. Okay? And you'll probably break your hand. Okay? Now, people who, fight for, they're professional fighters, they're going to use their hands from time to time. What keeps them from breaking them? They're wrapped. Yeah, that gives part of it. It also adds mass if you're a cheater. Okay, I don't know if you guys have ever seen, like, there's been a few scandals where they would weight the gloves of boxers, okay, so that the gloves were heavier, and protected the hands and was a heavier punch because the glove was heavier, okay? But also, they hit things all the time in training. Okay, they're working the heavy bag or the rhythm bag or whatever. Okay, every time you strike something, it causes little microfractures in your bones, and they heal back stronger, and your bones get more and more dense. Okay, and that can help, but it still comes down to simple physics. Your hand is lighter than most things you're going to hit with it. Okay, especially somebody's head. Okay, somebody's head is a lot heavier than your hand is. Okay, and all things being equal, as Newton's third law says they must be. Okay, whatever force you exert is going to be exerted back. Okay, that is Newton's third law. Every action has an equal and opposite reaction. Okay, so if you exert a force on something, it is going to exert a force back on you. Okay, it's why if I push on the wall, I move backwards. Okay, when I exerted a force on the wall exerted a force back on me. Now, the wall is not going anywhere, although it did flex because I'm huge. Okay, but obviously the wall isn't going to move, right? But it'll flex a little bit. Okay, I'm going to move because I'm lighter. Okay, that's why a smart car can't win a collision with a semi-truck. Okay, the forces, believe it or not, this is the part people can't get their head around. The forces are equal. Okay, if you have a smart car and a big bus and they hit each other, the force on the bus and the force on the car are the same. What's different is the acceleration they experience. The larger one experiences much less acceleration. We watched the video of the Mercedes and the smart car having that collision, okay? And by the end of the collision, the smart car was moving backwards. The Mercedes was still moving forwards because it was more massive. They were going the same speed when they collided. Forces are equal, okay? That's the part that people have trouble understanding because it doesn't feel that way. It doesn't look that way, okay? When you run into somebody bigger than you and you bounce off of them, okay, it doesn't feel like the forces were equal, but they are. You're just smaller, and so you have a greater acceleration. Does that make sense? Okay, this kind of goes back to something we were talking about before, like why you don't see small linemen or small sumo wrestlers, okay, or things like that, because in a situation like that, mass matters. Okay, you want to exert forces, but you don't want to go anywhere. Okay, so that's what normal force is. Every action is an equal opposite reaction. All right, so when we're talking about like linemen in a football game, okay, their whole job is to push people around. Okay, either get to the quarterback, okay, if you're the defensive line, or protect the quarterback if you're the offensive line. But when it comes right down to it, it's just about pushing on each other. Okay, if you're the lighter lineman, okay, unless you have really, really good technique, you're not going to be moving forward. You're going to get pushed backwards. Okay? It's just about pushing people around. Okay, small sumo wrestler, big sumo wrestler. Forces are equal. Small guy goes bouncing off. Okay? All right, this is also how rockets work. Okay? A balloon, when it comes right down to it, is a rocket. Okay? When you blow into the balloon, you put a whole bunch of air in the balloon. What is the air doing to the balloon? Right, and what is the balloon doing?
Go up.
Well, if I'm holding
Pushing
it,
back.
pushing back. Okay, if I'm holding it so no air can escape, those forces are equal. If I let it go, the forces are still equal, but now the air can escape. So the air accelerates out the opening and the balloon accelerates the other way. Okay, this is how rockets work. Okay, if you're launching something into space, you've got the reactants in there, they're creating pressure. The pressure is escaping out the back of the rocket engine, okay, and it's accelerating the rocket upwards and the gases downwards. Okay, this is actually why rockets accelerate more and more and more as they go. As they use up their fuel, they become lighter. Okay, so a rocket's acceleration gets greater and greater and greater, partly because it's further away from Earth and gravity has less of an effect, but it's also getting lighter as it uses its fuel. Okay? It's actually something that all rocket scientists have to bring into their calculations. The mass of the ship is not constant. As it uses its fuel, the mass of the ship gets lighter and lighter. And if they don't account for that, okay, they can miss where they're supposed to go. Make sense? All right, so that's an action-reaction situation. Okay, you are in the boat without a paddle. You're that far from the dock. Can you jump from the boat to the dock? Let's say you're a good jumper and you could jump that far. Okay, could you jump from the boat to the dock? Almost everyone, when I ask this question, shakes their head no, okay? Because they picture what will happen as you run along the boat. What will the boat do? The boat will move backwards, okay? Is that a Newton's third law situation? The boat's moving backwards because you're doing what to it? You're pushing it backwards. But when you push it backwards, it pushes you forwards. This is absolutely possible. You could absolutely make this jump because when you push on the boat, it has to push back. Now, I'm not saying this would be easy. Probably some of us would leave our teeth in the dock. Okay, probably wouldn't make it. It would be unpleasant. Okay, but physically speaking, Newton's third law says you can do this. Now, here's the way you create an advantage for yourself. If you just push horizontally backwards, yeah, the boat's going to push on you, but the boat is lighter than you. It is going to accelerate backwards. It is literally going to slide out from under you. What if you push downwards? Right, and it's not just the boat now.
Water.
It's all the water under it. Does that increase the mass you're pushing against? Absolutely. Yes, if you just push straight backwards, you're probably going to put your teeth in the dock, okay? But if you push at an angle like this, which is what you would do if you were jumping, you're not going to try and just jump horizontally, okay? You're going to push slightly downwards, you get all of the mass of the water underneath as well, okay? It doesn't change the force that you would experience, it changes what the boat would do. Okay? The boat's not going to move as much because it's not just the boat, it's all the water under it. Okay? If you exert 100 newtons down, you're going to get 100 newtons the other way. Okay? All that would change is what happens to the boat. Okay? Absolutely 100% possible, okay, using Newton's third law. Okay, what gets crazy about Newton's third law is this. There's no new math. When you actually break down a Newton's third law question, you're just doing Newton's second law math. It's sum of all forces. You just have to take into account that if you do this to the right, it's doing it to you to the left. Okay? But it still comes down to you're drawing a free body diagram, okay? You're doing a Newton's second law kind of calculation. It just adds in a action-reaction pair kind of thing to the question. Okay, so let's say you're an astronaut. Okay, this is why, and I'm going to give you a piece of information. If any of you ever become an astronaut, never do an EVA without something heavy on your belt that you're willing to part with. Okay, like a big wrench, okay, or something like that. Always take that with you. Because if you're out there, and we remember this from when we watched Woody float away, okay, if you're out there with no ability to exert force, you're just going to keep going at a constant velocity because the net force will be zero and you have no way to exert a force on anything. But if I get separated from my ship and I have a wrench, I can take the wrench off my belt and do what with it? Throw it. Because when I exert a force on the wrench exerts a force back on me, accelerating me in the other direction. Now, I'm not saying this is going to be huge. Okay? It's not going to be a huge acceleration. But if you were stationary and your ship was stationary, it would be enough. How long does that acceleration last?
Forever.
Not the acceleration, the velocity will.
As long as you're applying the force.
As long as you're applying the force. What does it mean you have to do with the wrench, though?
Make it like,
Yeah, I wouldn't throw it like this because that will bring a rotational aspect to that force, right? The wrench will rotate and you'll rotate the other way, okay? I would say like put it in your center of mass and kind of do like a chest pass with it, get rid of it, okay? But that's the key. You have to get rid of it. Right? I've had people who are like, well, why would I let it go? Why wouldn't I just keep doing that? And the answer is, so this is what you'll look like in space. Are you going to go anywhere? No, because every time the wrench gets to here, what do you have to do to it?
Pull it back.
Pull it backwards to stop it. You're just dancing in space, and you look as silly as I just did, okay? Dancing in space. So no, you actually have to sacrifice the wrench. You have to let it go. Okay? You have to push it as hard as you can so that it pushes you in the opposite direction. Okay, so simple Newton's third law question. You're in space, you push on the spacecraft. Okay, so you have a mass of 92 kilograms. The ship has a mass of 11,000 kilograms. All right, you push with 36 newtons this way. What does the ship do?
push from 36 back.
Right, pushes with 36 newtons this way. Do you both accelerate? Yeah. Are your accelerations the same? No. Because when it comes right down to it, what we have here is force 1 equals negative force 2. So the force exerted on the ship equals negative the force exerted on the astronaut by the ship. Okay, well, that means the mass of the ship times the acceleration of the ship equals negative mass of the astronaut times acceleration of the astronaut. Everybody okay with that? So, since I know what the force is, Could I calculate the acceleration of both of them? I absolutely could, okay? So for the ship, 36 newtons equals 11,000 kilograms times the acceleration of the ship. Are we talking a pretty small acceleration here? We absolutely are. Okay, so 36 divided by 11,000, whoop, not 10,000, 11,000. Okay, that's pretty small. It's 3 millimeters per second squared. Not much, right? It also doesn't last for very long, because it only lasts as long as the astronaut is pushing. But does it change your velocity a little bit? It does. And if you are doing that at the beginning of a trip that's really, really long, could that affect whether you arrive at your destination or not? It could. That triangle, right? It's the same angle all the time, but you're not going where you thought you were going because of that little change in velocity. Okay? And the longer you go at that velocity, the further from the place you thought you were going you will be. Now, for the astronaut, okay, negative 36 equals 92 kilograms times the acceleration of the astronaut. Well, the acceleration of the astronaut is going to be a lot bigger. Okay, 0.39 negative meters per second squared, so backwards. Okay. Everybody all right with that? And again, that acceleration only lasts as long as the force is being exerted. Once he's no longer able to push on the ship, he's got whatever his final velocity was forever. Unless he has the wrench. Then he can maybe do something about it by throwing the wrench in the other direction. Okay? Questions on how that works? Okay. All right. Walking. Walking requires you to use Newton's third law. Okay? Right now, walking back and forth in front of you, okay? I'm propelling myself forward by pushing on the floor. Which way am I pushing? Okay? Actually, I'm pushing this way, okay? Like, if you look at what my feet are doing, I'm pushing. I'm trying to push the floor that way. What is the floor doing? Pushing me this way. Okay, now, let's extrapolate. What's the floor attached to? The ground. Is the ground the earth? Okay, I accelerate forwards. I exert a force on the earth that propels me that way. What did I do to the earth? I propelled it the other way. Uh-oh. I just accelerated the earth. A lot? No. Okay, I'm minuscule. The earth is massive. What if everybody did? What if I got everybody in the whole world all together and we all jumped at the same time? Could I knock the earth out of orbit? What if we all ran the same direction? Could we reverse the spin of the earth like Superman? No, we couldn't. Why? Because even the entire population of the Earth's mass is nowhere near the Earth's mass. Okay? Do we exert a little bit of force? Sure we do. Okay? But it's so minuscule that it just doesn't make any difference, even if you got everybody to run in the same direction. So I'm going to show you this video that it was a Super Bowl ad years ago, and it resulted in me looking like as crazy as I am, yelling at the TV. Okay? Not because of the game, but because this ad is stupid, and people would believe it. Okay? So that ad started this whole thing about like, oh, if everybody jumped in the same place, we could knock the earth out of orbit, and we could spin it the other way, and the sun would rise in the west instead of the east. It's ridiculous. Okay? There's no way, A, we could exert enough force to do that. The moon has a bigger effect on the Earth's rotation than we could ever have. Okay? And secondly, the mass of the Earth is enormous compared to the mass of humankind all together. Okay? And then there's the practical parts of getting everybody to run in the same direction without running into things, okay, and stuff like that. Plus the Earth is round, that old chestnut that the Earth is round, okay, and if you're not at the equator, then you've got vectored forces that are not rotating and all that weird stuff. So yeah, it doesn't, it's not, no. Yes, I accelerate the Earth, sure, but it doesn't matter, is what it comes down to. Okay? Plus, I mean, the soil and the mantle, like you've got a separation, right, of the mantle between the core, and the mantle is liquid, and yeah, it's, yeah. Okay, now, here's a use of Newton's third law. Okay, I don't know if you've ever seen the people who, you know, tow those little U-Haul trailers down the Deerfoot at 130, okay, and they're towing it behind like a little Honda Civic, okay? It's craziness, even though it says right on the trailer, there are many stickers that say don't exceed 80 kilometers an hour in this thing, okay? Well, the big problem with those trailers is that most cars that will tow the smaller trailers don't have a way to apply the brakes. Okay, if you tow a trailer with a truck, okay, or a semi-trailer with a semi-truck, there's a way to actuate the brakes. Okay, with pickup trucks, it's electric. Okay, you plug in the thing at the back of the truck, and it'll send power to the trailer's brakes, and the trailer's brakes will apply. You want that to happen so that it doesn't jackknife. Okay, that is, you stop and the trailer keeps going, a Newton's first law situation. Well, for most of the vehicles that will tow these small trailers, they don't have a brake hookup in the back. Okay, no way to send electricity to the trailer brakes. So they use a action-reaction control system. It's a spring. So there's a spring inside the hitch. When the car in front slows down, the trailer in back doesn't. And it pushes on the tow vehicle. And then the tow vehicle has to push back. That spring is applied to the brakes. So when you slow down, it pushes against you and you push back, which applies the brakes. Uses Newton's third law and a spring to apply the brakes on the trailer. Works fine, provided you're not making any emergency maneuvers and you're not going 130, okay, with everything you own in that trailer making it heavier than the vehicle that's towing it. Okay, that's not a good situation. All right, but it's a Newton's third law application. Okay, everybody with me there? All right, we are going to look at a classic Newton's third law problem, the multiple boxes problems. I'm going to get you to write that one down, and we'll get started on it, but we probably won't finish it today. Okay, so a question like this is both a Newton's third law question, and it's a Newton's second law systems question. Okay, when it comes right down to it, we've got this system, 23 kilograms worth of mass, being accelerated at 1.5 meters per second squared. Okay? At this point, that's all we know. I could calculate the net force on the system at this point if I wanted to, because I know the acceleration and I know the mass. That won't help me. Knowing the net force on the system won't help me, because this question wants to know a force within the system. Okay? It wants to know a force acting on a single box within this system. It wants to know how hard is C pushing on box B. All right, so these ones involve kind of the most reasoning when putting together free body diagrams. Okay, so the question wants to know how much force is exerted on box C, or by box C, on box B. So we're talking about a force that's acting on the middle box. Is there anything to do with the first box that's going to help me here? Not really, right? If I'm looking at box A, okay, I know it's 8 kilograms. There's the applied force that's acting on the entire system, pushing directly on that box. What else is acting on that first box? Okay, gravity and normal force. They offset each other, so they cancel. Okay, you're right. You're absolutely right, though. It does. Okay. Does box A push on box B? So box B then pushes back on box A. So this force here would be the force of B on A. All right. None of those forces are the ones the question wants me to solve for. Okay. And they're not part of an action-reaction pair. Okay? What I mean by that is when we talked about the astronaut and the ship. Okay? The force exerted by the astronaut was the action. The force exerted by the ship was the reaction, and those forces were
The same.
the same, but opposite in direction. So we can always look for an action-reaction pair. All right, box A, not gonna help me. Okay, box B. Box B is 10 kilograms. Okay, what's pushing box B forward?
Box A.
Box A, yeah, the force of A on B. Okay, and this is its action-reaction pair, the force of B on A. Doesn't really help me. Okay, what's this force?
C.
C. That's the force that C exerts on B. Is that the one the question wants me to find? Okay, maybe I'm getting a little closer here. Can I calculate the net force acting on this box? Okay, this box is accelerating at 1.5 meters per second squared to the right. Okay, and the box has a mass of 10 kilograms. So that means that the net force is 15 newtons. Okay, that's the M times A part of it. Here's the sum of all forces part. The net force is the force of A on B plus the force of C on B. Well, at this point, I'm pretty screwed. I know this force, but I don't know either one of these. And I have no way to get the force of A on B. So I can't get the force the question wants using this box. Is there one more box in this system?
C.
Okay. C is at the end of the system, right? So it's a 5 kilogram box. What's this force?
1.5 meters per second.
That's an acceleration. What would I call this force? What's pushing box C that way? Okay, this is a frictionless surface. There's nothing in front of box C. Are there any forces acting backwards on it? No. Okay. Question wants the force of C on B. The only reason this force exists is because B pushes on. That is an action-reaction pair. They are equal in magnitude, but opposite in direction. If I can find one, I know the other. Agreed? So, this is the only force acting on this box. Is it also the net force acting on this box then? Can I calculate the net force on that box? Mass times?
Acceleration.
Okay. When it comes right down to it, that is the only calculation you'll do in this question. You will go 5 kilograms times 1.5, and you'll have your answer. Did you have to do a lot of figuring to get there? That's
Good
what
morning,
makes the
everyone.
third law difficult.
Can
We'll
we
talk
please
more about
stand
that
for the
tomorrow.
flag of the Angelus?